Phase diagrams are a way to illustrate the different phases of a substance as a function of pressure and temperature. So here we see, for example, a phase diagram of water. To the left of the diagram is where you find the solid form. To the right and to the bottom is gas or vapor phase. And in between is liquid. If you move from left to right, you pass from a solid to a liquid to a gas. So what phase exists at 10 degrees Celsius and 500 torr of pressure? Well, 10 degrees Celsius is about here. If we go up, somewhere around here is 500 for torr, and that would place us in the liquid phase. Be careful when you look at the y-axis. Quite often the pressure axis is not actually a linear axis. It may be logarithmic, for instance. When we look at a phase diagram, there are some things we should notice. Of course, we have these lines labeled A to B, B to C, and B to D. Above the line A to B to D, you can have a solid or liquid form of that substance. Below that line, the substance will be a gas or a vapor. If the system is right on a line, then the two phases are in equilibrium. If you're right on the fusion curve, B to C, then solid and liquid phases are in equilibrium. If you're on the curve A to B, then solid and gas forms of the substance are in equilibrium. And finally, if you're on the curve B to D, the vapor pressure curve, the liquid and the gas forms are in equilibrium. So if you cross these lines, that's when you have phase changes. So crossing the fusion curve, you can have melting or freezing going in the other direction. Crossing the vapor pressure curve, you can have vaporization in one direction, liquid to gas, or condensation, gas to liquid. And crossing that curve, remember, can occur by changing temperature or pressure. You could be in the liquid phase, lower the pressure and cross that curve and have vaporization. And then for the sublimation curve, of course, going from the solid side to the gas side would be sublimation. Crossing in the other direction would be deposition. Another feature of the phase diagram, which is not always shown, is the critical point. The critical point is labeled C in this diagram. And liquids cannot exist at temperatures greater than the critical point temperature, no matter what the pressure. Remember, the x-axis is temperature. So if you're to the right of the critical point, then you cannot have a liquid. So the critical point temperature is the temperature at which a gas cannot be made to liquefy, no matter how great the applied pressure. The critical pressure is the pressure of the critical point, and it's the minimum pressure that must be applied to bring about liquidification at the critical temperature. What does this mean? If you have gaseous, this is the phase diagram for water again, this would apply to other substances as well, but if you had the gas form of water at 100 degrees Celsius but low pressure, and you increased the pressure, you would cross the vapor pressure line and condense the water by increasing the pressure. If you're to the right of the critical point temperature, then increasing the pressure will not form a liquid. So if you increase the pressure above the critical point temperature, you will not liquefy the substance. So at the critical point temperature, that's the maximum temperature at which you can liquefy the substance by increasing the pressure. And that's the pressure at which the liquid will form. So this region of the phase diagram is where we see supercritical fluids. So what does it look like when you form a supercritical fluid? Well, in these figures, you can see a window looking into where the pressure is being increased and carbon dioxide is present. And you can see a meniscus. There's liquid carbon dioxide below, and above is gas phase carbon dioxide. And there's this equilibrium between the phases. As you increase the pressure, you start to see the meniscus disappear. Then finally, it disappears when it becomes a supercritical fluid. So why is that? Well, the gas pressure is increasing until the density becomes equal to that of the liquid. And then there is no more distinct difference in phase. It's one continuous phase. The liquid and the gas have become the same density. And so that is a supercritical fluid. So here is another phase diagram for carbon dioxide, and you can see the supercritical fluid region in the upper right, where the critical point is. The vapor pressure curve ends, and that's our critical temperature and pressure. Supercritical fluids can dissolve substances like a liquid, and that's where they are a little different than a gas. A gas you don't usually think of as capable of dissolving substances other than other gases, like a liquid can. When you form a supercritical fluid, though, it has the density of a liquid, so it can act as a solvent, actually, but it can effuse like a gas. And property of supercritical fluids is while they can act as a solvent, their density is variable. You can apply subtle changes in pressure and change the density. Carbon dioxide is used in the dry cleaning industry where high pressure above the critical temperature is applied. You have to have very high pressure, but the temperature is reasonable, 31 Celsius. But if you can increase the pressure of the carbon dioxide, you can make the supercritical fluid. It's a non-polar substance, so it will dissolve greases and remove those from clothing. And then when you decrease the pressure, the carbon dioxide will just escape as a gas, so you don't have any solvent to dispose of. This leads us to a couple of terms: permanent gases and condensable gases. Technically, a permanent gas is one in which the temperature, the current temperature, is greater than the critical point temperature. If you increase the pressure, you will not liquefy it if you are above the critical point temperature. But a lot of times these terms are used in reference to room temperature. If you have an oxygen gas cylinder, it contains a permanent gas. Oxygen is a permanent gas. And why is that? The critical point temperature of oxygen is well below room temperature. So exerting a pressure on it when you fill the cylinder with oxygen gas will not liquefy the oxygen. You can measure the pressure of the tank while you use it. And as the gas comes out, the pressure in the tank will decrease, and you'll observe that. That seems fairly obvious, but it's true for permanent gases, but not for condensable gases. Condensable gases are gases that have a critical point temperature greater than 25 Celsius. So you've probably seen propane tanks before, and if you have one that's filled and you move it around, you can feel liquid sloshing around in there. That's because, being a condensable gas, room temperature is below the critical point temperature. And when we pack that cylinder with propane, it liquefies. And what is now in that cylinder? Liquid, and above it, some vapor, propane in liquid form and in gas form. And of course, what is the pressure of the gas phase propane going to be? It's going to be the equilibrium vapor pressure of propane for that temperature. So let's say we're right at room temperature, 25. There is an equilibrium vapor pressure of propane, and that's what's going to be the pressure of the gas in the cylinder. The rest of it will be liquid phase. Now, as you use the propane, the gas phase propane above the liquid maintains its equilibrium vapor pressure. So there's no point in having a pressure measuring device on this cylinder because you are always going to read one thing: the equilibrium vapor pressure of propane. It's not going to decrease as you use it until the very end when the tank is just about out and there's no more liquid left. We should look at the vapor pressure curve in a little more detail. You probably remember that term, vapor pressure curve. That's the curve we've talked about before. The temperature increases and the equilibrium vapor pressure increases. And these curves are described by the Clausius-Clapeyron equation. Here, the vapor pressure curve in the phase diagram that you see is this same vapor pressure curve for water in this case. I want to discuss this vapor pressure curve, however, because the y-axis has a dual role. In one application, when you're looking at the phase diagram, this pressure is the total external pressure that we use to determine whether the substance will be a solid or a liquid or a gas. And so this y-axis is the total external pressure, and you use that pressure and temperature and you evaluate using the phase diagram. It can also be used as the equilibrium vapor pressure of just the substance itself as a function of temperature, like we did before when we were considering vapor pressure curves on their own. So the pressure in that case on the y-axis is the equilibrium vapor pressure of that substance. Okay, so let's take a look at this phase diagram of water and ask a couple questions to consider these two applications of the y-axis. So what phase is water when we are at 78 degrees Celsius under 1 atmosphere of pressure? So I've added these lines here. You would say, oh, we're at 78 degrees, 1 atmosphere, 760 torr, and that places us right here in the liquid region of the phase diagram. So the answer would be a liquid, and we use the y-axis as the total pressure. But what if I said, what is the vapor pressure of water? Well, now we say it's 78 degrees, and we come up to the vapor pressure curve, and then we come over to the y-axis and say, what is the vapor pressure of water above the liquid at 78 degrees? And that would be 330 torr. The triple point is another feature of the phase diagram, and that's where all three phases are in equilibrium: liquid, gas, and solid. So I said before that if you're on any of these lines, the fusion curve, sublimation curve, or vapor pressure curve, the two phases on either side are in equilibrium when you're on that line. But if you're at the point, it's three phases that are in equilibrium. And when I first heard about the triple point, I thought that this was fantastic. It must be incredible to see. It's actually not all that exciting. I mean, it is exciting that it exists, but it's not like watching fireworks go off. It's not like you're seeing things freeze and boil at the same time before your eyes. It's not what it is at all. The triple point is difficult to reach unless you know how to do it. And think back to our discussion we just had about the dual role of the y-axis, pressure, and what that means. You have a total pressure over the liquid, and you also have the vapor pressure of the gas, which is adding to the total pressure in a way. And so this system has to come to equilibrium. You let it sit there, it comes to equilibrium. And if you try to change the pressure to reach the triple point, and then change the temperature as well, you're going to have the system react by adjusting its vapor pressure, and it's going to be difficult to actually get right to the triple point. So there's a trick to it. And the trick is to make sure that the only gas above the water is water vapor itself. And what does that mean? That means that the total pressure above the liquid, we're using water as an example, this would be true for other substances. If you set it up like this, the only gas above the liquid is the vapor of that liquid itself. And so the total pressure is the equilibrium vapor pressure. So using water, we can have some liquid water here, and it's in equilibrium with its vapor at any given temperature. So let's say we start at 78 degrees. We're right on this line. This 330 torr is the vapor pressure of water, but since it's the only gas in there, that's also the total pressure. So what do? You start cooling this system down. You lower the temperature, and if you stop at any point, let it reach equilibrium, what is the pressure going to be? It's going to be the equilibrium vapor pressure. So by slowly cooling it down and letting it reach equilibrium all along the way, you are following this line until you cool it down till you reach the triple point temperature. What will happen at that point? Well, you'll have liquid and gas in equilibrium still, but now you're going to start to form some solid phase of that substance, water in this case. What does that mean? You're going to get some ice in the water. You'll have all three phases in equilibrium. The water and the vapor will be in equilibrium. The water and the newly formed ice will be in equilibrium, and the ice, the solid, and the vapor above it will be in equilibrium as well. So you reach that triple point by following this line, by having the only gas be the vapor of that substance. So here's what a triple point cell looks like. This one just has the liquid and the vapor in it. The only gas in here is the vapor of this liquid. And then if you cool it down slowly, you'll start to form some ice in this region. You'll have all three phases in equilibrium. And so these triple point cells are the best way to calibrate thermometers. If you have two substances for which the triple point temperatures are known, you have 2 points in which you can use to calibrate a thermometer. You've probably thought about this in the way it's usually done, where you might use boiling and freezing points to calibrate a thermometer. Take water, you could say, oh, I'm going to boil it. It boils at 100 degrees Celsius. If I boil it and I have a thermometer, I can say, oh, that temperature should be 100 degrees. And if I freeze the water, while it's freezing, it should be 0. And so I can make my scale on my thermometer doing that, those two experiments. But these points, the freezing point and boiling point, are pressure dependent. And so that's an extra variable that can be difficult. The triple point has one specific temperature and pressure. If you reach the triple point, there's only one temperature at which that occurs. So if you need a super accurate thermometer, this is how you calibrate it. Carbon dioxide, I'm going to use as an example to illustrate what you can use the triple point for, and that's to compare it to 1 atmosphere, standard atmosphere on Earth, and ask yourself, can that substance exist as a liquid? For CO2, carbon dioxide, the answer is no. You see a picture of dry ice there, and it's subliming into the gas form. You cannot melt carbon dioxide, dry ice, on Earth unless you have some special conditions where you increase the pressure. Why is that? Well, here's one atmosphere. Here's one atmosphere that you find at the surface of the Earth. Where's the triple point? It's at 5.1 atmospheres for carbon dioxide. So that tells us to have a liquid, the lowest pressure we can have is 5.1 atmospheres. That's the triple point pressure. Below that, there's only two phases you can have, solid and liquid. So if we increase the temperature of dry ice, we will sublime it. If we want to melt solid dry ice, we can't just raise the temperature at the surface of the Earth. We also have to raise the pressure.